We're now going to look at the case where the steric number for a molecule is 5. An example of this is a molecule called phosphorus pentachloride, the Lewis structure of which looks like this. In this case, if we're going to calculate the steric number, we're going to take the number of atoms attached to our central phosphorus, which is 5. We'll add to that the number of lone pairs on the central phosphorus, which is 0. And we get, of course, a steric number of 5 when we take the sum of those two. The atoms in this particular molecule are going to orient themselves around what is called a trigonal bipyramid. We'll take some time and describe the trigonal bipyramid to you here. It's called a bipyramid because you can envision this as being two pyramids, and trigonal because both pyramids have a triangular base. So let's look at this. What I'm going to do is I'm going to remove this particular bond here and just place the resulting structure on a piece of paper like this. And what we see, if we do that, is we see 4 atoms that lie in the plane of the paper. This would represent the chlorine atoms. This would represent the phosphorus atoms. These all lie in the same plane, and they all form a pyramid with this top chlorine that's up here off the plane of the paper. They form a pyramid where this is the apex of the pyramid. These form the corners of a triangle, and if we imagine lines going this way, we have a pyramid. Well, of course, we can flip this over and do the same thing in the other direction, of course removing this bond in this case. And we see on the other side we have another pyramid. So we have 2 pyramids, or a bipyramid, both pyramids of which have a triangular base. So I'm just going to orient it this way. And in this case you can see the apex of both pyramids. I'm holding them with my hands. And then the base of both pyramids I'm sort of rotating so that you can see all 3 atoms in the base of the pyramid. Now in this particular structure there are going to be 2 different types of, we'll call them terminal atoms. So the chlorine atoms sit at 2 different types of positions. The ones that my hands are touching right now, we would call them the axial positions. They sort of represent the axis, the top and bottom of the axis that I am rotating the molecule around, kind of like the rotation of the Earth. The Earth rotates on an axis. So this atom and this atom would represent axial positions. These positions here that I'm rotating, these 3 here, these represent equatorial positions, or sort of like the equator of, you can think of that, of the Earth. There's 3 equatorial positions, and there's going to be 2 axial positions in a trigonal bipyramid. Now you should recognize there's 2 different types of angles that we're going to have to think about here. The first angle is going to be the angle between an axial position, the central atom, and a equatorial position. And if we look at that here, in this orientation, we can see a equatorial, central atom, axial angle. That's 90 degrees. That's going to make a 90-degree angle. I'm going to take off the 2 axial positions, and I'm going to place the resulting structure here so we can get a good idea of what the equatorial central atom, equatorial bond angle looks like. That's 120 degrees. So this structure here with the axial positions removed, this reminds me of the trigonal planar orientation that we see with the steric number of 3, where our bond angles are 120 degrees. Of course, when S equals 5, though, we also have these axial positions in place. And in the molecule PCl5, where all positions on the electronic geometry, this would be a trigonal pyramidal electronic geometry, when they're all occupied by atoms, the geometry of the molecule and the geometry of the way that the electrons orient themselves, they're the same. Well, there's some other cases where S equals 5. Let's look at, for example, sulfur tetrafluoride. The Lewis structure for this substance looks like this, where we recognize there's a lone pair on the central, sulfur. If we were going to calculate the steric number for this particular molecule, we'd have 4 atoms attached and 1 lone pair for a steric number of 5. And just like before, we're going to end up having the electron pairs orient themselves in this trigonal bipyramidal arrangement, where I have my hands are holding atoms in the axial position, and I'm rotating the equatorial positions. And we can see that one of the equatorial positions that's located close to the camera right now, one of the equatorial positions has a lone pair there. And that actually ends up being important to stick that lone pair there, because this, you remember the lone pair electrons, they exert the most electronic repulsion on the other pairs of electrons that exist in the structure. And because of that, we want to get this as far away from all of the other, in this case, bond pairs as possible. And that's done by placing the lone pair not in an axial position, but rather in an equatorial position. Now again, we're going to remember that this lone pair of electrons is going to exert a little more pressure on these bond pairs that exist. And so the equatorial central atom equatorial bond angle, that's going to get it's going to get shrunken a little lower than 120 degrees. And the axial central atom equatorial bond angle, that's going to get squeezed in a little smaller than 90 degrees. If we go to describe the shape of this particular molecule, remember we're going to ignore the lone pair of electrons. And if we describe this particular shape, it kind of looks like a seesaw, where this is sort of the base of the seesaw, and these are the 2 people sitting on the ends. So we have a seesaw type structure. Finally, we'll take a look at chlorine trifluoride, the Lewis structure of which looks like this, in which we're going to need to recognize that there are 2 lone pairs on the central atom. And if we're going to find the steric number for this particular Lewis structure, we're going to recognize we have 3 atoms attached plus 2 lone pairs for a steric number of 5. This particular molecular structure is going to have the electrons orient themselves this way, where what I'm doing is I'm rotating in this plane here. I'm rotating a lone pair and another lone pair and a bond pair. Those are all being rotated in the equatorial plane. So all of these are roughly a little smaller, but they're roughly 120 degrees from one another. And then these 2 atoms here are located in the axial positions. So we have an axial position here and an axial position here. And this is the way the lone pairs are going to orient themselves into a trigonal bipyramidal electronic arrangement, so that we can get these lone pairs as far away from everything else as possible, because remember, these are going to show more repulsion than the bond pairs. So we want to get these as far away as we can from everything else, and by placing them in the equatorial position, we're able to do that. Now, the only bond angles that end up resulting in this particular orientation result from a equatorial central atom axial position. Again, equatorial central atom axial position. And these are normally 90 degrees, but because of this extra lone pair repulsion, it gets squeezed down a little tighter than that 90 degrees. If we want to describe the molecular shape, we're going to remove the lone pairs, and we see that the structure that we're left with looks kind of like a T. So we call this a T-shaped molecular structure, even though the electronic geometry is trigonal bipyramidal.